Today we're going to be working on rate times distance problems. And rate times distance problems aren't that different from the problems we were just doing. We can use a chart in most cases to help us organize our information. Here's our first problem. And this is the kind of problem we indicate as motion in opposite directions. So bicyclists Brent and Jane started at noon from points 60 kilometers apart and rode toward each other, meeting at 1:30 p.m. Brent's speed was 4 kilometers per hour greater than Jane's speed, and we're looking to find their speeds. So we want to make a table to organize our information. And what are we talking about? Well, we're talking about Brent, and we're talking about Jane. And what are the aspects of those two that we're talking about? Well, we're talking about their speed. We'll call that their rate. And we're talking about the time, how long they were driving, and we're talking about their distance. And we know that with rate times distance, it's rate times time equals distance. So now we want to figure out how we fill these things in. Well, just like with our previous problems, there are some things we don't know. And we can tell right at the end, what are we looking for? We're looking to find their speeds. So that means we don't know their speeds. So we can set their speeds as our variables. Let's say that Jane's speed is r. Well, if that's true, and Brent is going 4 kilometers faster than Jane, then Brent's speed is Jane's speed plus 4. Now there's this issue of time. Well, they don't give us a specific time, but they do give us information about time. They say that they started at noon, and they met at 1:30 p.m. Well, that's an hour and a half. So if I do my time in terms of hours, I can say 1.5 hours. And that's the same for both. And if rate times time equals distance, then when I fill in my distance category, all I have to do is write 1.5 times r plus 4 for Brent and 1.5 r for Jane. Now we've got our table filled out, but the point is figuring out, okay, how does this all relate? How does this all go together? And this is this issue of motion in opposite directions. This is the thing we want to think about. So what I like to do is draw a picture. And rather than expose you to my own drawing, let me see if I can bring a picture in here that might help. There. Here we've got Jane and we've got Brent, and they're bicycling towards each other. And if you notice, they started at 60 kilometers apart from each other, and Jane rode 1.5 r distance, and Brent rode 1.5 times r plus 4 distance. So if we put their two distances together, based on this drawing, we should see that they should equal 60 kilometers together. So that sort of defines an equation for us, because if we think about it, we realize that Jane's distance, or 1.5 r, plus Brent's distance, 1.5 r plus 4, has to equal the distance they travel together, or how far apart they are, which is 60 kilometers. And then we can go ahead and solve. 1.5, do distributive property here, 1 plus 1.5, that's going to give us 3r. 1.5 times 4 is 6 equals 60. We can subtract 6 from both sides, and we get 54. 54, 3r equals 54. So 3r equals 54. Divide both sides by 3, divide by 3, and r equals 18. All right, in this problem we have motion in the same direction. So we're talking about a helicopter leaves Central Airport and flies north at 180 miles per hour. 20 minutes later, a plane leaves the airport and follows that helicopter at 330 miles per hour. How long does it take the plane to overtake the helicopter? So in this case, we want to still set up our chart. In this case, we're talking about, it's still a rate times distance problem, and we're talking a helicopter and an airplane. And we're talking about the rate of these two things and the time that they travel and ultimately the distance. Okay, so here's our basic chart. Now we just want to fill in as we go. So the rate for the helicopter is 180 miles an hour. The rate for the airplane is 330 miles per hour. So in terms of time, they don't really give us time, but they give us how the times are related. Because it says 20 minutes later, the airplane travels. So if the helicopter's time is, let's say, T, or let's set the airplane's time to T. If it left 20 minutes later, that means the helicopter has 20 minutes more time. But we can't say plus 20 because 20 minutes doesn't mean 20 or 0.2, right? Because an hour is 60 minutes, so we have to write what 20 is compared to an hour. 20 minutes of an hour is 1/3 of an hour, so it's T plus 1/3. 1/3 of an hour, 20 minutes. And then to find distance, we do that same equation. Rate times time equals distance. So we have 180 times T plus 1/3, and we have 330 times T. Now the key with this is, okay, what's the relationship here? How do these things relate to each other? What's the equation we can write? Well, if we read the last part of the equation, how long does it take the plane to overtake the helicopter? This is another instance where a picture is going to do us some good. So let me see if I can grab us a picture. So here's a picture of how what the helicopter and the plane look like. Noticing that the helicopter has a little bit of a head start, the plane's following behind it, but the plane's going much quicker. So the idea here is when one overtakes the other, they're actually at the exact same point. The distances are the same. The distances are equal. So that's what allows us to set up this equation. Because if I know the distances are equal, I can take the expressions for the distances, 180 T plus 1/3, and set them equal to each other, 330 T. Distributive property gives me 180 T plus 60 equals 330 T. I can subtract 180 T from both sides, which gives me 60 equals 150 T. Then I just divide both sides by 150. And if we simplify this, we end up canceling out the zeros. So we have 6 over 15, and both are divisible by 3. So 2/5. Now, 2/5 doesn't make a whole lot of sense until you realize you're talking about hours again. So it's 2/5 of an hour. And that's fine. You can leave it like that. If you want to go through the process of figuring out what that is in terms of minutes, you can do that, but I'm fine with 2/5 of an hour. I think that's an acceptable answer. It's going to be about 24 minutes, but 2/5 of an hour is fine. And that's how you solve motion in the same direction. Notice the last problem was motion in opposite directions. This is motion in the same directions. And we have one more motion type problem. This type of problem is called round trip. And it says, a ski lift carrying Maria up a slope at a rate of 6 kilometers per hour, and she skied back down parallel to the lift at 34 kilometers per hour. The whole trip, the round trip, took 30 minutes. So you have to figure out how far did she ski and for how long. So let's set up a chart again. Now this time it doesn't really make sense to do Maria and something else because it's all Maria. So you want to figure out, okay, what are the two situations we're talking about? Well, we're talking about the ski lift up and the skiing back down. And we want to fill in the information we know about each one of these. Again, the labels aren't going to change. You're dealing with rate times time, times distance, times time, times time equals distance. And we have to figure out what we know about each one of these things. Well, the first thing, rate. Let's see. The ski lift carried Maria up the slope at a rate of 6 kilometers an hour. So we know she's going up at 6 kilometers an hour. And she skied back down parallel to the slope, to the lift at 34 kilometers. So up is 6, down is 34. The whole trip takes 30 minutes. So if we say that the time going down the slope was T amount of time, we can say that the time going up the slope was half hour minus t, whatever time remained after we took away t amount of time for the 30 minutes down the slope. But we can't write 30 because we don't want to talk about it in minutes because our speed is kilometers per hour. So how much is 30 minutes of an hour? It's 1/2. So we'd say 1/2 minus t. So distance is going to be 6 times 1/2 minus t, and distance here is going to be 34t. Now again, the point of this is figuring out, okay, how do these two distances relate? How far is it up versus how far is it right back down? Well, if she's going up and back down the same mountain, parallel paths to each other, it's going to be the exact same distance, right? She's going up the mountain, she's coming right back down the mountain from one point to the other, right back and forth. So their distances are going to be equal, so we can just set them equal to each other. This should be a t. So we can say 6 times 1/2 minus t equals 34t, which if we solve, 3, right, distributive property, 6 times 1/2 is 3, minus 6t equals 34t. Add 6t to both sides, 3 equals 40t. Divide by 40, divide by 40. T equals 3/40ths? Well, it's not a pretty number, and in terms of an hour, in terms of distance in this, no, right, in terms of time, right, we're solving for time. In terms of time, like how much time it is, it doesn't come out all that pretty. But we can just say 3/40ths of an hour. But then we want to figure out, okay, if it's 3/40ths of an hour, let's actually figure out what the distance is. And so to do that, we can use 34 times t, this equation for distance, because remember distance is the same, and just plug in 3/40ths and solve. And we end up with something pretty ugly, 90, 100, and, well, anyway, it simplifies to about 2.55 kilometers if you simplify this math. Okay, so 3/40ths of an hour is fine, 2.55 kilometers is fine for distance. So those are the 3 types of distance problems you're going to be talking about, rate times distance problems tomorrow. We're going to be talking about motion in opposite directions, motion in the same directions, and round trip.